Correct. In the table column, present noun also is there. Present noun. If you click that button, present noun. Okay. Present noun is there. If you click that button. Correct. And let me share. So now is there. You can see can you see my screen?
Yes, sir.
Oh, I see. It's asking me what would I like to share my screen. Share. Okay, now I have to minimize and then okay, excellent. And there it is. Is that in order? Okay, so we'll wait for a few minutes. I'll start exactly at 11:30. Okay, your time. Actually, we wait for another 5 more minutes, 5 to 6 minutes. Then, so once more. Yeah, it's not 8 to 9 minutes. 11:30. Good. So your voice is little else. Okay, well, you tell me when to start. You tell me.
Exactly at 11:30 we can start, sir.
Okay, well, you tell me when it's 11:30 on your watch.
Okay, sir.
Thank you. Okay, sir. Sure, sir. So you possibly can increase the volume, sir. Let me try. I don't know how to do that. Let me escape and I guess I have to go back here to here. Now I'm increasing my volume, but I don't know how to increase my volume to you. Maybe I should just sit closer. Is that okay? Can you hear me?
Yes, sir. Yes.
Yeah, I can't. When I click it, is it clearer now?
Hello.
Yes, sir. Yes, sir. Hello. It is clear.
Thank you.
Hello. How is it, sir?
Let me.
Morning, sir. Sir, when you registered, sir? Okay, sir, do you have a WhatsApp to you? This one? We have already mailed you, but I think so. It is in scam or spam or something. Just tell me the WhatsApp number. I'll be sharing the link to join. Sir. Yeah, you will be receiving from Srinath or else Sudarshan, sir. The both email. Okay, sir. Is it your WhatsApp number, sir? Whatever you have said, call me. The same. Yeah, I'll be messaging.
అంటుంది. వాడు ఏ వాడు చిన్న తెచ్చుకొని ఒక ప్లేస్ లో పెట్టి చూడు మళ్ళీ ప్లేస్ రాసేసుకొని రాకపోతే కంటిన్యూ అంటుంది. బయట ఎందుకో మైసూరే వాడేదాన్ని కాదు నాన్న కెమికల్స్ వస్తుంది అందుకనే అది వాడుకుంటున్నాను. ఇంత అంతా కాదు కెమికల్స్ ఇప్పుడు పెట్టుకున్నా స్నానం చేసేటప్పుడు రుద్దినా మనకు సోప్ అంతా రెడ్ అవుతుంది మైసూర్కి కాదు అది ఏ సోప్ అన్నా అయిపోయింది మనం మాట్లాడిన చెప్పకపోతే
Hello, can you hear me? We're going very quiet.
Yes, sir.
Oh, you can hear me. Can you hear me? We're going very quiet. Yes, sir. Oh, you can hear me.
Prof, I think you can start now.
Okay. Can you hear me clearly? Is everything okay?
Yes.
And you can see my screen as well.
No, I can't see. Can't see your screen. Can you please share it again?
Yeah, I thought. Sorry, I didn't realize I'd lost your screen. Try it.
Screen, sir. No problem, sir.
Can you see the screen?
I'm able to see your screen. No? Yes, sir.
Okay.
Participants are requested
Participants, can you please?
to use balance. Pin.
Okay. Can everybody see my screen? I hope so.
Sir, can you please enlarge it?
I can see it. It's small.
It's small. Well, I don't know how to make it larger. I'm seeing a large screen here.
Sir, now it is.
Sorry.
Yes, sir. Now it is large, sir.
It's clear and it's large and everything's okay.
Yes, sir, we can see it.
All is well. Okay. I need this pointer, so I'm gonna keep. Sorry. Where are we? Yeah. Good morning, all. I guess it's 11:30 in India, and
Sir, 1 minute, sir.
everybody's
Sir,
out.
1 minute,
Sir, can we?
1 minute, sir. Shall we start the program, sir?
Oh, please go ahead. Sorry.
Yes, sir.
We can't see your screen properly, full screen.
You can't see it.
At the bottom of the screen on your right, if you click on present now, you will see something says your entire screen or window tab. So
Is this in PowerPoint or in?
no, once you are on the Google window.
When I'm on the Google window, let me try that. So I have to get out of here, go back to Google, go here, and say your
At
screen.
the bottom,
Resume your presentation.
yes, so that will work.
So that are you now able to see my screen?
Yes, you just need to put it now on the full screen on PowerPoint.
Yeah, I will. Can everybody see it clearly now?
Yes, it's okay now.
Okay, excellent.
Thanks.
Okay, so Dr. Sudarshan, over to you to start the lecture. Thank you.
Yes, sir. Small introduction is there. Srija, please start now.
Yes, sir. I request all the participants to keep your mic mute and video also. I request all the participants to make your mic. Hello all, hope all are safe. Myself Srija Murthy, Assistant Professor, Civil Engineering Department, VJIT. Good morning to Dr. E. Sai Baba Reddy sir, Director VJIT. Dr. A. Padmaja ma'am, Principal VJIT. Dr. Pallavi Badri ma'am, Head of the Department, Civil Engineering VJIT. Dr. Yunus Salim sir, today's speaker, my dear colleagues, and all the participants from all over the world attended. I extend my warm welcome to all of our one-day international seminar on advancements in concrete technology, organized by Department of Civil Engineering, VJIT, in association with ICA Student Chapter, Telangana. Now I request Dr. Pallavi Badri ma'am, Head of the Department Civil Engineering, to address the participants.
Thank you, Srija. Can you hear me?
Yes, ma'am. Yes.
Yes, madam.
Yeah, okay. Thank you. Respected Director, Professor E. Sai Baba Reddy sir, Institute Principal Dr. A. Padmaja ma'am, today's Honorable Resource Person Dr. Yunus Balim, Professor, Construction Materials, School of Civil Engineering, University of Witwater Strand, participants from the several universities from India as well as from other countries, my dear colleagues, a very good morning to all. On behalf of Organizing Committee, Civil Engineering Department, VGIT, I am pleased to welcome you all for this one-day international webinar on advances in concrete technology. I am very happy to share with you all that around 800 participants are taking the benefits of this event. And it's really happy news for us that VGIT is growing at the global level also. As a matter of fact, Professor Yunus picked a very apt topic to address the civil engineers and the other professors, as temperature changes plays vital role in the strength parameter of any construction material. And I hope this lecture will be useful to all participants in their learning process. Here, I would like to express my sincere gratitude to our director, sir, Dr. E. Sai Baba Reddy and Dr. Padmaja ma'am, principal, to join with us and motivating us for organizing such knowledge sharing events. Without wasting much time and making you all waiting, I welcome you all again and I will proceed for the webinar and also wishing for individuals health safety at this particular situation. Thank you. Thank you, Srija. Please take over the event. Thank you.
Thank you, ma'am. And now I request Dr. A. Padmaja ma'am, Principal VJIT, to deliver the keynote address.
Yeah, good morning everyone, and I'm Dr. Padmaja, as Dr. Pallavi has already introduced. First of all, I would like to congratulate Dr. Pallavi, Civil HOD, and convener of this international seminar, Dr. Sudarshan, for organizing this wonderful one-day international seminar on advancements in concrete technology by two eminent speakers, Dr. Yunus and Dr. Shen, in association with Indian Concrete Institute ICI chapter. I don't know much about the topic, but I can say that there has been a rapid advancement for the last 3 decades in the concrete technology. And many of the researchers are also going in this direction. I hope today's two sessions would benefit all the faculty members and the students, and some of the faculty members may be working in this area may get some valuable inputs from the today's session. I once again congratulate the department team for organizing this wonderful session, and also as it is a remarkable day for the civil engineering department that 800 registrations are there for today's session, it seems, as Dr. Pallavi told. So I hope all of you will utilize this one-day session very effectively and come out with some new innovations or new direction of research in this area in the department also. Thank you very much, and I also welcome Dr. Yunus for this VJIT wonderful session at VJIT Civil Engineering Department. Thank you very much, Pallavi.
Thank you, Principal ma'am. Actually, please mute your mics. Participants can clearly hear the content what we are going to deliver. And now it's my privilege to introduce our speaker, Dr. Yunus Balim sir, Professor, School of Civil and Environmental Engineering, University of the Witwatersrand, Johannesburg. And he was going to deliver a lecture on developments in understanding heat flow and temperature development in large concrete elements. Dr. Yunus Balim holds BSc, MSc and PhD degrees in civil engineering from University of the Witwatersrand in Johannesburg. After 6 years in the construction industry, he was awarded the Portland Cement Institute Research Fellowship based at WITS in 1989, was appointed as a lecturer in 1992, and he currently holds a personal professorship in civil engineering at WITS. He was the head of the School of Civil and Environmental Engineering from 2001 to 2005. His research is mainly in cement and concrete material science, and he has held a National Research Foundation rating as a researcher since 1994. He is a senior member of RILEM and has served on a number of their international technical committees. He served as the founding president of the African Materials Research Society and held the Bram Fisher Oxford Fellowship in 2000. Between 2006 and 2012, he served as the Deputy Vice Chancellor, Academic, and the Vice Principal at WITS. He served 2 terms as a member of Commission for Higher Education in South Africa and was chair of the Higher Education Quality Council. He is presently a professor in civil engineering at WITS and is member of the Council of Humanity, where he also serves as chair of the Assessment Standards Committee. In 2012 and 13, he was the chair of the board of the National Institute for Higher Education in the Northern Cape and has recently ended a 6-year term as the founding vice chancellor of the New Sol Plaatje University in Kimberley. Thank you, sir. We welcoming you and thanks for joining with us.
Thank you very much, and thank you for that. You didn't need to read my whole biography, but I think you should all be able to see my screen now. I think I'm getting used to this. Can everybody see my screen? And I hope all is well.
Yes, sir. We can be able to see your screen, sir.
Thank you very much. So, colleagues, well, first of all, thank you. Today, I should just mention it's a public holiday today in South Africa. It is a day we commemorate Women's Day. And it's particularly important to me that we started this seminar by having 2 women lead us into the discussion. So thank you very much for that. Thank you also to Dr. Sudarsan and to the team at VJIT for inviting me to present this lecture. I'm going to, just as an apology to start with, I'm going to try to squeeze a lot into 45 or 50 minutes. And so I'm going to ask you to bear with me. But my main intention is in putting this lecture together was to give a sense, particularly to the young people who I hope are attending, emerging scholars, emerging academics, researchers who are considering careers, of the possible opportunities for research in this area, which has occupied my mind for quite a long time. And I've done a fair bit of work. And even as I start, I want to acknowledge all the students and the colleagues who have worked with me in taking us along this journey of trying to better understand heat flow, heat development, but also temperature prediction in large concrete structures. What I will do is briefly really just go through a short discussion on cement hydration and importantly the rate of heat evolution. I'll give you a sense of how we measure the rate of heat evolution for cement, and then I'll talk a little bit about the forms of expression of the heat rate function, particularly as we try to solve the Fourier equation for heat flow in concrete. I'll give you an indication of a development of a finite difference model that I developed and its operation, and then some experimental verification of those results. I'll show you some of the effects of different cement and construction variables on temperature development. And then I'll end with a more recent development that I've been working on, which is to allow for the possibility of sequential construction. And then I'll open to some discussion. I aim to keep this to about 45 or 50 minutes and hopefully leave enough time for discussion and questions and so on. And of course, importantly, for criticism. Thank you. So what I'm showing on the slide here is a polished section of a typical South African cement clinker. Remember, this is not cement, this is clinker as it comes out of the furnace. This is a polished section. In other words, we're looking at it under the microscope, but using reflected light rather than transmitted light. And the sample has been etched with hydrofluoric acid. And what you see, what I wanted to show you here are really the dominant crystal forms of cement. There's these very large tricalcium silicate crystals, angular, well developed. You can see the angled structures. And then there's these more rounded nodular dicalcium silicate crystals. There's the interstitial matrix material, which is really the brownish stuff that you can see here, the tricalcium aluminate phases, and the whiter, lighter areas are the aluminoferrite phases. And those really form the four dominant crystal structures of cement. My scale marker is a 25 micron, so you can see that particle over there is probably about 40 micron across. And if you imagine that the average particle size of cement is around 5 micron, that particle will go to form quite a few individual, or rather that crystal will form quite a few individual cement. Notice also the intergrowth. There's dicalcium silicate growing inside of the tricalcium silicate. Here's a dicalcium silicate crystal that's intruding into a tricalcium silicate crystal. And here is an air void in the clinker. And this is a fairly typical South African clinker. Lots of tricalcium silicate, a little bit of dicalcium silicate, and very well-defined interstitial material. I thought to show you an example of a clinker from India. These are air voids on the sides here. This is air voids. Sorry, just to remind you, this scale marker is twice as long as that one. So that's 25 micron. This is 50 micron. And even in this sort of smaller magnification, you can see very large deposition of dicalcium silicate, or what we call B-light. And it's a characteristic of cements in India, which seems to indicate slower cooling rates of the clinker. There are some tricalcium silicates. Here's a big crystal here, here's one up here, there's tricalcium silicates up here. But predominantly, we see lots of dicalcium silicates in cements made in India. There's obviously the cement industry has a strategy. Remember, it's pyroprocessing that determines crystal formation. But it's something I want to use because I'll show you later how it affects heat rate. Remember, again, just to remind you, when you add cement and water, you produce calcium silicate hydrate, which is the binding material, the stuff that binds all your aggregates together, and turns this wet, soapy material into a solid stone-like material that we use for construction. We also produce lots of calcium hydroxide, and about 25% of all the cement that is hydrated will be crystalline calcium hydroxide. You also go from a crystalline cement to an almost amorphous calcium silicate hydrate. Very poor crystal form, but this is really the material that binds everything together. And then what I wanted to highlight is that in that process, you produce about 300 kilojoules per kilogram of cement hydrated, kilojoules of energy. It's about, just to put it in context, it's about enough energy in a kilogram of cement to boil your egg. If you put it, in fact, if you cast your egg in cement paste, a kilogram of cement paste, you could have a boiled egg the next morning. You may have difficulty getting it out, but the egg will boil. The pore water of we're typically dealing with an alkaline material, but the important thing I want to focus on right now is the cement heat that is developed. This is a fairly typical Delaroy produced this diagram a long time ago. And this is a plot of the rate of heat evolution. It's not the total quantity, it's the rate. And what we see is an initial rapid rate of heat evolution, which is caused by the hydration of that whitish material that I showed you, the aluminate phases. Yttringite then forms, and everything stops and settles down. And this is the time when, after mixing, you still have some time in which to allow your cement your concrete to be cast, compacted, etc. And then you get initial set, the tricalcium silicates, the halides, start hydrating very rapidly, and you get a peak heat rate, and then there's a decline. You don't always see the shoulder, but that happens when there's a conversion of etringite to monosulfate. And here on this declining limb, descending limb, it's mainly the B-lights that are hydrating. And the important point I wanted to make here is that when you measure 28-day strength of concrete, the biggest contributor is really the tricalcium silicates. And that's in this part of the curve. So as we just keep that, sorry, go ahead.
Sorry for the distance. Actually, your screen was minimized. Can you please enlarge it?
I have no idea how that happened. Let me try again. It seems to be that there you go, resume. No, somehow or the other, it stops. It sort of it stops the presentation on its own. I don't know why it's doing that. But let's try. Is that better now?
Yes, sir. Yes, sir. Now it was visible.
Okay, please let me know when. Let me know when that happens again. Okay, just shout at me. Thank you. Because it doesn't show anything on my screen. And so I wanted now to give you a sense of the fact that if we imagine a two-dimensional block of concrete, let's assume a very large foundation cast on a rock foundation, then what we need to do if we're going to determine the temperature development, we really have to solve the Fourier equation, and I'm showing it to you in this case in 2 dimensions. That's the density of the material, specific heat capacity, and then the change in temperature with time as a first order differential, thermal conductivity, the change in temperature with position as a second order differential. And then importantly, dq by dt, which is the curve that I just showed you, and that's the rate of heat evolution from the hydrating cement. So that's this term here, and I'm going to spend some time discussing how we determine this term, and then how we find a normalizing form of expression. The point to bear in mind is that if you have a large block of concrete like this, at point A, the temperature will rise and then decline in that form. At point B, which is closer to the surface, the temperature will not rise to the same level. The concrete will cool quicker, and you will get back to ambient temperature much quicker than you would at the center. 2 important things to bear in mind with stress development. During this phase, when the concrete is getting warm on the inside, the concrete is expanding internally and is being restrained by the cooler outside. So the outside of your element goes into tension. And what will likely to happen is you'll get surface cracks. They don't go very far. They tend to be quite small, but that's because the surface is in tension. After you pass this point when the inside is cooling, the surface goes into compression because the concrete inside wants to shrink. And that puts the inside into tension. And if cracking happens at that phase, you are more likely to get larger cracks. They tend to be unseen. And if it is a dam structure or a liquid-containing structure, it may in fact be a cause of deterioration, durability problems, maybe even leakage. So that's really why we're interested in the subject of heat development. Okay, so on to a conversation about how we determine this parameter, which is the rate of heat evolution from cement. The first thing you need to do, if you do it very quickly, is you need to measure the temperature change of the hydrating cement sample. Okay, if you know the specific heat capacity of the cement, you can multiply by the change in temperature, normalize for the mass of the sample divided by the mass of cement, and that will give you the amount of heat per unit mass of cement. Okay, and then you can determine the rate of heat evolution dq by dt. Sorry, all okay. As being sort of a numerical integration of the heat function. You of course have to keep all the heat in. You must make sure that you don't have exchange of heat. So isothermal calorimetry is more commonly used. This is where you monitor the temperature, the amount of heat you need to extract in order to keep the temperature of the sample at the same level. We, however, chose to use an adiabatic approach, which is where we insulate the sample thermally from its environment, which means that all the heat that is generated stays inside the sample. And I'll show you how we did that. We developed this, it's really a completely homemade calorimeter. It works very well. So what we have is we have a sample of concrete. This is real concrete, so it's a stone, it's aggregate with water and cement. That's about 1 liter of concrete there. We have a temperature probe in the concrete, and that is sitting inside of a bath of water, which has a heater element and a stirrer. The motor is outside of the water so that it doesn't add heat to the water. The computer system monitors the temperature of the concrete sample, switches on the heater or off to make sure that the water is exactly at the same temperature as concrete. And if you can manage to maintain these two temperatures the same, then you've got adiabatic conditions. In other words, there is no heat exchange between the sample and its environment. The system works very well in principle. However, because these thermal probes are not quite accurate and all measurement instruments have inherent error, it is possible that you could get harmonic signal responses between these two samples. And what happens is either the sample temperature is cooled because of the water not keeping up, or the water temperature chases the sample temperature. We solved that problem by adding a pocket of air around the sample to act as a dampening function in that harmonic response. And it sorted out the problem. Of course, it reduced our sensitivity slightly, but what it does do is sort out the problem with harmonic responses. And we get very good results out of this. This is just a closer view of the sample holder. There's a cotton wool plug here, so we get no pressure development as this air warms up, but we do keep the temperature of the air controlled in response to the water. The sample is sealed inside, and that's how the probe operates. Using that piece of equipment, it's possible to develop a curve like this, where you plot temperature versus time, and you can get very good results. And as you can see from this, it actually continues. Hydration is continuing after we've got 45 hours. Hydration is continuing, but as I said, we lose sensitivity with that instrument, and so the instrument tends to lose its ability to measure small changes in heat evolution. Nevertheless, with that, you can, using this equation which I showed you a little earlier, that's the change in temperature term, you can transform that into a total heat function. And if you differentiate that curve, you will get a heat rate, which is really similar to the de la Roy curve I showed you a little earlier. Initial activity of the illuminate phases, cooling down period, and then initial set happens, and then you get mainly A-light or tricalcium silicate hydrate, and then a declining limb with mainly dicalcium silicate hydrate. You see the heat rate in this case. where what we did was we created a time scale where a second can be longer or shorter depending on the temperature. And that's called maturity. And we use the Arrhenius function, which is a fairly common function that is used in chemistry. And we normalize the Arrhenius function to 20 degrees C. Effectively, what we are saying is what would the hydration state have been had we kept the temperature to 20 degrees C. And that's really all this is doing. This equation requires the energy of chemical reaction of the cement, and we take a single value that probably smooths over all the different reactions that are taking place. That's the Rankine constant, R. And you can see this 293 is simply Kelvin temperature at 20 degrees C. And if you use that expression, it is possible to change the axes on your time heat rate curve so that it can be normalized. And I'll show you how we demonstrated that. And so effectively what we do is we normalize the heat rate curve. Instead of dq by dt, we use dq by dm. M is maturity. The problem, of course, is that the world doesn't move according to imaginary timescales. So you have to find a way back into clock time. And the way you do that is simple, it's through a dot product. You get back to dq by dt by multiplying dq by dm at any time by the rate of change of maturity at that particular time. And you can see here, if when you consider this, I'm sorry I'm going through a very complex discussion in a fairly short period, but what we're effectively doing here is accounting for the time temperature history. And that then brings us to dq by dt, which accounts for time temperature history. It may sound a little bit abstract, but I'm going to show you that it actually works. And so what we did was we took the same concrete, put it into our calorimeter, but started the test at 3 different temperatures. One at 13 degrees, one at 21, and one at 29. It's all okay. Okay. And as I expected, what happened was we got three different heat rate functions. So for the same concrete, with a different time temperature history, we produced 3 different dq by dt curves. When we normalize the x-axis, which is in time, to a maturity axis, and we normalize the heat rate, which is in joules per second, to joules per maturity second, we were able to normalize those 3 curves. And so those 3 curves, in fact, collapsed onto a single curve, more or less, which now allows us to determine a normalized dq by dm. You can see that this curve sort of lying around the level of this one, which started at 21 degrees, because we're bringing everything to T20 hours. And so what we now have is an ability to produce a normalized heat rate function, which then allows us to start thinking about how we solve the Fourier equation. This is just maturity heat rate curves for typical cement. And what I wanted to show you here is that although all of these, for those of you, all okay? For those of you who are counting, there are 8 heat rate curves here. And this is 8 cements from 8 different plants in South Africa. They're all sold as Portland cement, but actually they have very different heat rate characteristics. This one that happens to stand out just has a particularly larger amount of magnesium in it, periclase. But otherwise, you can see that the peak heat rates occur at different times for different durations, and they heat and cool at very different rates. So when you buy something called Portland cement, don't imagine that they're all the same thing. Here's an example of 3 cements from a manufacturer in India. It happens to be the same manufacturer, but from 3 different plants. What is interesting here is that this manufacturer is actually producing quite consistent cements. What I also wanted to show you is this lower peak heat rate than what you saw with the South African values. And that, I think, is as a result of the preponderance of the dicalcium silicates rather than tricalcium silicates. I'd now like to turn to development of a temperature prediction model. I use the finite difference approach. Finite differences work in these kind of problems mainly because our dimensional variations are large. You don't have to go to millimeter level of position differences. And our time intervals are large. We talk about hours rather than minutes in time intervals. So I developed the model for a block of concrete that is cast on a rock foundation and discretized into finite differences, fixed finite difference in X and Y, subjected to an external air temperature that varies in some sinusoidal function. And I just to remind you, in one dimension, I'm interested in the temperature at point M that has neighbors M minus 1 and M plus 1, and intermediate points M plus a half and M minus a half, separated by distance delta x. I'm doing this in one dimension. Okay? The second order differential is the difference between the first order differential at that point and the first order differential at that point divided by delta x. The first order differentials are determined by the temperature difference between that point and that point, and similarly that point and that point. And from there you can get a second order differential that is based on the temperature at M, the temperature at M minus 1 and the temperature at M plus 1 divided by delta x squared. Okay? And then of course you can approximate the time differential as the temperature at point M in time interval N and at point M in time interval N plus 1. So I'm doing a forward step calculation, divided of course by delta T, whatever delta T we choose in the model. It's a forward step calculation, and that essentially is the principle for developing the equations. We set up the equations for this kind of nodes, where P is the point of interest, an internal node separated by 4 neighbors, a bottom edge node separated by 3 concrete neighbors and 1 rock neighbor. Sorry, that's not a telephone, it should be a delta x. An edge node separated by 3 concrete neighbors and subjected to heat flow to the environment at a rate that is determined by coefficient of heat exchange, and then a corner node separated by only 2 internal concrete nodes. And that really is it's not very complex. I wrote the code in Excel using Visual Basic. I must promise you I'm not a very good code writer. I'm a competent one, but I'm not a very good one. So for those of you who are better code writers, you probably laugh at my code, but it actually, it works reasonably well. And of course I fitted a sinusoidal curve to the ambient temperature. This is just to show you how it works with real temperature. It's not great, we could certainly do better than this, but that's the model that we used for ambient temperature variation. We cast a block of concrete in the lab, and we used only half a cubic meter of concrete. I say only, that's still sort of 1.2 tons of concrete. But we arranged it so that we had 1,000 millimeters in this direction, 1 meter, 700 millimeters in this direction, 700 millimeters in this direction. Okay, and then we heavily insulated these 2 surfaces. So what we did was effectively in the Z direction, we produced an infinitely long element because no heat or very little heat was flowing out of these faces. All heat flow was through these faces, and so we effectively created a 2-dimensional problem. We instrumented the center of this with temperature measurement devices, and we set up the probes here at these points that I show here. The top was exposed, the sides had formwork for 18 hours, and then the formwork was removed. And what the model does is when you remove the formwork, we change the value of H, which is the coefficient of heat exchange to the environment. And we measured and then ran the model. And as you can see, we produced fairly good results. That's the central probe. The green is the measured values. The red is the modeled values. That's the bottom probe. That's 200 millimeters from the top. Very poor modeling at the surface, and that is really because we didn't account for boundary conditions that included heat loss through radiation. I have since improved the model to account for that, but this was quite a time ago, and you can see that there's clearly a boundary condition problem with the model. Just to give you some effects of using the model, of course, some effect of difference. So remember I said to you that not all Portland cements are born the same. Here I chose 3 different sort of a low, medium and a high peak heat rate cements. And you can see that in a large concrete element, 4 meters by 3 meters, using 200 kilograms of cement per cubic meter, that if you use those 3 different Portland cements, those are the heat rates you'll get at the center of the block, or rather, at the center across a cross section, when the peak temperature occurs. So with clinker D, which is the low heat, you get a lower temperature rise, and the peak heat occurs, or peak temperature occurs at 108 hours. With clinker K, you get the highest temperature at 94 hours. Okay? However, if you're casting a small element, 0.5 meter by 0.5 meter, and you're expecting a higher strength, so you're using 475 kilograms per cubic meter, you get an almost, 6 or 7 degree difference in the peak temperature, just by changing the type of cement that you use. All of them called Portland. Fineness of grinding is very important. Here we took 2 cements, clinker A and clinker B, and we changed the fineness from below 2640 square centimeters per gram to almost 5,000 square centimeters per gram, and you can see how the heat rate function changes. More importantly, not only does the peak heat rate increase, the peak also occurs a little earlier. And you see that with both of these cements. And here you can see this is the nominal specific surface area. That would be typical for South African cements. If you bought a pocket of cement in South Africa, it would probably be ground to about 3,200 square centimeters per gram. That is a very, very finely ground cement. You can see the effects of the peak heat rate. So if you want to control peak heat rates and temperatures in your concretes, be careful with grinding. I also want to show you the effects of these are the same cement from India, but one of them ground to what would be normal in South Africa, 3,200, I think normal in India as well. And then one ground to almost 4,000 square centimeters per gram, which is not as high as what you saw earlier. But look how significantly different the heat rates are. And I think, again, that this is an effect of the high calcium silicate in the clinker form in the Indian cements. And it would certainly be worth exploring what's going on here and what effect it has on heat development in large concrete structures. Just the effect of some supplementary cementitious materials, slags going from 80% GGBS to 0% GGBS, 100% cement. And you can see the very significant effect on heat rate. Interesting that with fly ash, it has a similar effect in reducing heat rate, but it also delays slightly the peak heat rate. That's very interesting. And as expected, silica fume has almost no effect on heat rate. So if you're going to think about reducing peak temperatures in large concrete elements, fly ash and slag, I imagine rice husk ash would have a similar effect. Would be something really interesting to look at as well, and other pozzolanic materials would have this kind of effect. And you want to maximize the amount of these supplementary cementitious materials. Well, just to, and I'm going to end this point in another 5 minutes or so. One of the things that I've been trying to do is to account for solar radiation. And this was the problem of dealing with the boundary condition problem. And so what we did was on the roof of our building, we measured solar radiation in Johannesburg. And we importantly measured net radiation. So in other words, we were counting for exit radiation as well as incoming radiation. And of course, the instrument we used was able to measure exit radiation and net as well. And that was an interesting parameter for us. And what I show you here is firstly, the black squiggle line here is the solar radiation coming in on the 18th of February. Remember, for us, this is summer. Our summer solstice will happen on the 21st of December. This was measured on the 18th of February. The reason that you get these up and down peaks during the day is because of cloud cover. This is really sort of our summer rains happen about October, mainly December, starting to close down, but Johannesburg typically has very strong afternoon cloud cover, thunder showers, etc. And so you see that here happening in the afternoon with lots of cloud cover. What I've done with the dots is I've added sort of a model that I've fitted to really just, it's a cosine function. Fitted to this curve for daytime solar radiation. And then I show you the model for 23rd of May, which would be a little bit after our equinox. Our equinox is about March. Well, I guess the world's equinox is in March. And then here on the 8th of June, which would be our winter solstice, which is about 21st of June. And you can see that the peak radiations are decreasing from summer to winter. That will probably be of the lowest daytime radiation value. We get much lower cloud cover in winter. And so I've decided to use these functions in the heat model in order to provide some assessment of boundary conditions as a result of solar radiation. Interestingly, at night, the exit radiation settles at around 80 watts per square meter. And it sometimes goes to 40, you get peaks. I'll have to talk to the geographers about the reasons for this kind of variation. But it's not unreasonable to think of it as a fairly constant nighttime value. And so taking this dotted line, which I show you here, I've inserted that function into the model in order to provide a radiation boundary condition for the top surface of the concrete. I've at this stage not accounted for radiation on one side only, and we will do that, get to that point a little later. The other thing that I've done is I've tried to account for sequential construction. Which is, you know, when people build dams or bridges or large foundations, you generally do not cast in one layer. And so the concrete is placed in sequential layers, mainly to allow the heat from the lower layer to dissipate. The problem is that depending on the time intervals of your casting sequence, when you place another layer of concrete on top of a previous layer that has not yet gone through its full heat liberation, you are now creating a situation where you're pushing heat from a lower layer upwards into the subsequent layer. And so it goes as you cast sequential layers. And so what I did was I've rewritten the model, and I must thank lockdown for that, because it gave me time to sit quietly and further develop the model. And we've in fact had occasion to use it on an actual structure recently. And I wanted to show you because thanks to a colleague that I worked with, we've been able to animate this, the development of the heat function. And here I'm showing it. I hope you can see it. You can see now we've sort of cast the first layer I'm going to try to pause. I don't know how to do that. Here it is. Sorry, let's go here. So you can see we've cast the first layer, and everything is at 20 degrees C. As a result of heat of hydration, the temperature develops and the colors are starting to evolve. You can see it's getting hot here. We've already reached 44.8 degrees C in the center of the first block. Sorry, this is the symmetrical center. So this is the block that we're modeling is 2 meter high and it's 12 meters wide. This is 6 meters away. So this is the center of the block. And each block represents half a meter intervals in X and Y. Okay. So that's 6 meters away from a side edge. It's quite cool on the side edge, cool on the top, getting hot in the center. And as we go ahead, we see the next layer arriving. We started at 20 degrees again. It was applied 5 days later. And we're already at 29 degrees internally. This surface, which was the top surface exposed to the air, is now at 39 degrees. And things are growing, and we can see this now is at 47 degrees, which is actually hotter than the bottom layer was at this point. And we get the top layer, the third layer cast, now already at 25 degrees. And this layer is getting sort of, we're getting to 48, 40, 49 degrees. By this time, which is about 5 days later, we're reaching about 52 degrees, having started at 20. The big heat is now, as you can see, in the second layer, and that is because it's drawing heat from the bottom and from the top. And so actually the model is actually able to reproduce these kind of parameters. It seems to be working. As I said, I've included the effects of solar radiation on the top surface, and that's working quite well as well. So we're making some progress. Of course, there's much further to go, especially in consideration of different binder types. Sorry, I should mention that this is, in this case, the model is using a concrete with 60% slag and 40% normal Portland cement, 42.5. And so, colleagues, I want to stop there. I think I've said a lot, and I have taken up your 45 or 50 minutes. I have given my presentation to Dr. Sudarshan, so I'm sure he'll circulate it to all of you. I've included just some references, mainly on the work that I've been developing, or the work that we've worked on. Remember, there are lots of other researchers who are doing some really exciting work. And you should, if you're interested in this area, you should certainly look at their work. And with that, thank you for your attention. Okay. I'm going to take back my screen now. If I can go back here and stop sharing. And go back there and say, Doctor, can I hand over to you to lead the discussion if there is? Tell me, I'm going to switch off my microphone. Tell me if you want me to turn off my camera.
Some questions are here for you, sir. Sir, you can unmute yourself.
Unmute, okay, thank you.
So the first question was, how about the maturity heat at normalized room temperature? How about the maturity at normalized room temperature? Sir, you have to unmute yourself.
I happened to mute. I apologize. What we did was we did normalize to 20 degrees C. But you don't actually have to normalize to 20 degrees C. You could choose any other temperature depending on the conditions. And in fact, it would be, if you happen to use an isothermal calorimeter, you would set your calorimeter to whatever room temperature you choose. I think the one that our colleagues use in South Africa is about 25 degrees C. But it doesn't really matter. All you're looking for is a normalized heat rate function at a particular temperature. and that's important. Let me say that the model that I showed you was used by, I have a research relationship with Professor Manu Santanam at IIT and Professor Ravindra Getu. And Manu's used my model for a large foundation that was cast in, I think it was in Chennai. And in fact, one of the comments about the model is that it tends to under-predict the peak temperatures. And I'm not sure if, of course, bear in mind that we're using South African cements, whereas in India they were using very different cements with very different characteristics. But I'm not sure that it relates to the way in which we are normalizing the heat rate function. I think the normalization process, we could probably look at it a little further, but I think normalizing to 20 degrees C has given us good results, and it's probably worth staying there. I hope that I've answered the question. Thank you.
Yes, sir. And the next question was, how was the consistency? How about the effect of copper slag in place, other pozzolanic materials used in the cement manufacturing, and its properties?
If I understand the question, what about the effects of different pozzolanic materials?
Yes, sir.
Yeah, we've tested fly ash, and slag is not a pozzolan, but we've tested slag as a latent hydraulic material. And as you saw, I showed you results for condensed silica fume, which of course has no influence in reducing heat rates. But it certainly would be interesting to look at other pozzolans. We've not had an opportunity to look at different pozzolans. There's a rice husk ash, there's natural pozzolans, etc. And I certainly, if anybody's interested, it would be a really interesting project to look at the effects of different pozzolanic materials in modifying the heat rate function of different cements. I mean, what would be a really nice ideal, long-term ideal, is to be able to take a teaspoon of cement and mixed with a pozzolan, and by measuring its chemical characteristics, be able to determine its heat rate characteristics, its strength characteristics, and so on. It's an unrealizable ideal, but really that's where, if we're going to find a bridge between what we do as engineers and cement chemists, that would probably be the basis for a collaboration or a conversation on how we understand the chemistry of cement and its effects on the macro performance of this material that we call concrete. Thank you.
Thank you, sir. Next question was, any other difference between Indian and African cement clinkers and plants production?
Yeah, as I said, I've given you a glimpse of it. We happened to have a student at IIT Madras who was doing his PhD, and he came to South Africa to spend some time with us here at our lab, and he used our calorimeter equipment. We at the time we didn't have isothermal calorimeters. I think today it'd be much easier to use an isothermal calorimeter rather than an adiabatic calorimeter. So, if you're interested in this work, I think there are a few isothermal calorimeters available in India as well. But he came here and he spent time, and that's the reason we happened to test so many, or rather a few, Indian cements. As I said, the main difference that we noted was the very high daylight content, and I think that's because of slower rate of cooling of cement clinker. It may well relate to the way in which the kilns operate in India, and I don't have enough knowledge on that. And then secondly was this very sensitive nature from a temperature point of view, and I imagine a strength point of view as well, of the Indian clinkers to fineness of grinding. The finer you ground, I imagine the higher would be your early strengths. And so Indian cements are generally, I think, more finely ground than you would find in South Africa. But that I'm speculating at this stage, and it certainly is something that we be worth looking at further. Yeah.
Thank you, sir. And does the pozzolanic materials have much effect on the materials we added in the replacement of certain combinations in concrete? If so, what are the effect of properties?
I'm not sure I understand the question, and if I did, I'm not sure I'm able to understand it. Beyond the measures that I showed, which was that the pozzolanic materials significantly depress the heat rate, the peak heat rate. And that is beneficial. I mean, we recently, not recently, a few years ago, we built a large dam in Lesotho for a hydroelectric power scheme and water supply, mainly to South Africa, where they ended up using 2.3 million cubic meters of concrete. And they put, as far as I remember, 70% fly ash into that concrete, but still needed post-cooling systems in order to take the heat out of the concrete. So plain Portland cement in these large concrete structures should never be used. You should never find yourself in a situation where with large concrete elements you're using plain Portland cement. Pozzolanic materials are almost compulsory. The effect on heat rate is the slower rate of hydration. And with these large concrete structures, particularly dams and so on, it's okay to think about 90-day strength rather than 28-day strength. Then in that case, pozzolans work very well. They produce calcium silicate hydrate at a slower rate. They evolve less heat. And so as a result, you can control your temperatures better. Remember, it's temperature difference that cracks your concrete, not absolute temperature. So what you want to do is minimize the peak temperatures so that you're able to minimize the temperature differences. The chemical effects of pozzolans would be a subject for a finer mind than mine in an area like cement chemistry or calcium silicate chemistry, and be interesting to do some work together with someone working in that area. Apologies, I don't have a proper answer for that question. Thank you.
Thank you, sir. And next was, what would be effect of cold temperature below 5 degrees Celsius on high volume fly ash concrete during setting?
I'm assuming that this is the initial temperature. Your question is related to the temperature of the concrete at the time of casting. Certainly the model that I developed is able to account for that. So you can change the initial temperature in the model, and you can set that. And you can very easily see the benefits of reduced initial temperature. If you took a very simple closed system and you didn't account for the temperature effects on heat evolution, if you very simplistically analyze this, and you said, well, in a given amount of cement, there is a fixed amount of energy that will be released during hydration. And if that amount of energy is able to increase my concrete temperature by, say, 25 degrees, then if I start at 5, the maximum temperature will be 30. If I start at 20, the maximum temperature will be 25. That would not be an unreasonable first analysis approach. Your error would be that you are not accounting for the effect of temperature in stimulating hydration, but it would be a reasonable starting point in the way in which you analyze this. The point I'm leading to is that reducing the initial temperature, floating temperature of the concrete will reduce the maximum temperature. And so it is a good idea. So we've had projects where people have used ice as the mixed water in the concrete rather than water. Somebody's microphone is on. Okay, but if you reduce the initial temperature, it will be beneficial. You'll slow down the initial rate of hydration. It will catch up, don't worry, but you will certainly end up with a better quality hydrate as well. So it is a good idea to chill the concrete if you can, if it worries you that that maximum temperatures will bother the potential for cracking. Yeah.
Thank you, sir. And next one was, how was the consistency in South Africa clinker be improved to match the Indian one with respect to heat curve?
I'm not sure that one clinker is better than the other. Be careful that we don't think about improving. Right? There's no reason why the Indian clinker should be improved or the South African clinker should be improved. What you need to do is ensure that you get consistent quality. That's more important. And I must say in South Africa, we're fairly consistent from particular factories or particular plants. So if you get your cement from the same plant during the life of your project, you're fairly confident that you're getting reasonably consistent quality of cement that will reproduce the heat and strength performance. If you change your plant, be careful, you may get a different quality and consistency of cement, and so you need to be careful of that. I don't know, and I'm not able to comment on the consistency of Indian clinkers. As you saw from the curves that I showed you for the same manufacturer, but from 3 different plants, from a heat temperature point of view, the clinker performed actually very consistently. So clearly, in those 3 plants, they're producing cement that is very, very consistent, and certainly more consistent than we've seen at South African plants. It doesn't bother us. The variation across plants doesn't bother us as long as you know what you're getting. That's what it means to engineer the material. So to engineer the material means to understand and to know exactly what it is you are working with, and then to respond appropriately for the needs of your structure of your construction project. Yeah. Thank you.
Thank you, sir. And next question was, which type of cement is mostly used in South Africa, and what type of special fibers used in concrete?
Sorry, what type of special?
Fibers.
Fibers. Okay. In South Africa, we generally use 42,5 or the 52,5 cement, and almost invariably it is blended with either fly ash or blast furnace slag. In fact, we've reached a stage in the marine environment. Sorry, in my other life, I also work in durability and deterioration studies. And with my colleagues at UCT, University of Cape Town, we've shown that, and one of my colleagues, Mike Otieno, who's also attending the seminar, has shown that slag and fly ash is so beneficial in marine environments in minimizing the risk of corrosion that in South Africa it is almost impossible to get plain Portland cement in a marine environment. Almost all your concretes will have at least 30% fly ash or slag in it. In an environment, there's still some people who use plain Portland cement, but well, even when I say plain Portland cement, it will have at least 10% either limestone or slag or fly ash in it. So in general, we're moving very strongly away from the plain Portland clinker cement. Fibers are used in very specialized applications in South Africa. And the one that springs to mind is in our mining applications, where in mine tunnel linings and so on, you need high ductility rather than high strength. And they tend to use steel fibers that are formed into sort of uneven, non-linear shapes to encourage bond. But that would be a fairly small application of concrete in South Africa in general. So fiber reinforced concrete is not a commonly used material in South Africa, yeah, except in special applications. Thank you.
Yes, sir. Next one is, what precautions must be taken to avoid rapid transmission of heat between layers of concrete laid in layers and the effect of transmission?
Yeah, remember the problem with concrete is that the thermal inertia is very high. So the thermal conductivity, the coefficients of thermal conductivity are actually quite low. To give an example, they monitored the temperature of concrete internally at the Hoover Dam when Hoover Dam was constructed. And it is estimated that it took about 22 years for the internal heat to be fully lost to the environment. So things happen very slowly in concrete, and heat doesn't move very quickly. The animation that I showed you raised the concrete temperature from 20 degrees C to about 52 degrees C. And that took, in that animation, about 15 days. the rate at which that heat will be lost to the outside is actually much, much longer. So you get a fairly steep heat curve initially and a much lower, shallower, steep cooling curve. I wouldn't sort of try to stop heat from moving between successive layers. In some ways, it is beneficial because it minimizes the temperature difference. So the upper layer almost has an insulating effect. If you're worried about the very last layer, one of the things you could do is insulate the last layer to minimize heat exchange to the environment. So heat exchange to the environment is probably more significant than heat exchange to subsequent layers of concrete. Yeah. But it is all driven by thermal conductivity, and the largest influence or variable that influences thermal conductivity of concrete is the type of aggregate that you use. The model that I use allows for different aggregate types. Sorry, I should mention the model is freely available. So anybody who writes to me and says, we'd like a copy of your model, by all means, I'll give it to you free of charge. In fact, I was thinking we should put it on our website. It's written in Excel, and as I say, it runs almost as a macro. With the code is written in sort of Visual Basic. Anybody who's good at writing that can get access to the code as well. If you change the code, just let me know. I'm interested in anybody who can improve the code. But the model is available free of charge. Don't even. And I'll send you a little book. We wrote a monograph on temperature development and how to operate the model. It isn't difficult. You select your parameters and then you run the model, and it gives you temperature profiles. So anybody who is interested in this from a research point of view, have no fear, it's available. Yeah.
Thank you.
Sorry, the other thing I should report, I'm sure that my South African English accent is a little bit difficult. So if there's anybody who doesn't understand the word I'm using or the way I'm pronouncing, please feel free to ask me to go over something. Thank you.
Thank you, sir. Next one is, how applicable is the model to high strength concrete with very high cement contents and very low degrees of hydration?
It's not an area that we've tried. I guess it's something that we should look at. Our focus has generally been on large concrete structures where high strength is not going to be a consideration. The problem with high strength structures is that the elements are usually smaller. You're probably thinking of thin layers or small concrete elements. And then my advice would be, don't use finite differences. You're probably at a phase where you need to use finite element analysis, because your space intervals are going to be much smaller, and you need to get higher levels of accuracy because things are happening much quicker than would be happening in a large concrete structure. So no, it's not an area that we've looked at. It'd be certainly an interesting development. Yeah.
Thank you, sir. And one more question and last question. What should be the age at which cubes of high volume fly ash concrete be tested to get the best result?
Please say that what should be?
What should be the age at which cubes of high volume fly ash? Age, sir.
Yeah. The age?
Yes, sir.
The age at which cubes of high volume fly ash. I'm not sure I understand that. But maybe you can interpret it for me?
What should be the age at which cubes of high volume fly ash concrete be tested to get the best result?
I really am not sure what best result means. And if I understand the question, it does require the design engineers to say at what age will they monitor cube strength for specification reasons. We generally rely on 28 days, and that's historical. There's no particular reason why we should use 28 days. But we rely on 28 days because historically that's the value we've used. We've also in the past found that by age 28 days, the future strength of the concrete is more predictable. It will increase, but it is more consistent in its predictability. There's too much variation at 7 days and 3 days to allow for that kind of confidence in our prediction of future strength. When you're using high volume fly ash or slag concretes, is 28 days appropriate? Maybe not. Maybe you could rely on 56 days, or as I said, when the engineers who worked on the Katsi Dam project looked at it, they said, well, the construction process is so long, we're quite happy to consider a 90-day strength as the acceptance level. Remember, what we're talking about is specifications for acceptance level. It's not anything about the inherent strength of the concrete. And it's okay to say, well, we'll accept a lower rate of hydration. At 28 days, we accept that there will be lower strengths, but we'll be more happy if you can give us the required strength at 90 days. There's nothing wrong with that. So I don't think there's maybe the question was worrying me because it refers to the best result. I'm not sure that there is such a thing called the best result. It's really what gives you the confidence in the future performance, long-term performance of a structure that you are building in maybe a year or two, and then expecting it to perform in service for the next 100 years. What gives you the confidence to say to a future generation that this structure will perform adequately? And that really is an engineering judgment question. And difficult as it may be, we mustn't forget that we have to apply our minds to the best of our engineering judgments. Thank you.
Thank you, sir. Thank you for answering all our questions with patience. Now I request Dr. Sudarshan, sir, to deliver the vote of thanks.
Shrija, I just wanted to have some discussion with sir. Sir, Professor Yunus, like your lecture, whatever you have given is quite informative. I am not the person from the structural engineering domain. My specialization is in geotechnical engineering. But small doubt is there with me when I was listening that. When we are doing the finite element analysis, sir, for the structures, basically we should go for the nonlinear analysis, right? To capture all the whatever scenarios, realistic model. So your model is working for that, or any what we can say the parameters you have given in that way in your model, sir? Sir, we cannot hear you.
Can you hear me?
Yeah, now I can hear you, sir.
Yeah. As I explained, we use finite difference, not finite element analysis. It's a similar thing, and all we're doing is we're differentiating between points, and we're doing sort of finite difference differentiation. The model is inherently nonlinear because, in fact, we're solving the Fourier function as I showed it.
Material knowledge.
The Fourier equation as we showed it. So it is inherently nonlinear. And I hope I'm answering your question, but we're trying to find numerical solutions to essentially a second order differential problem. And the results seem to be working. I'd be really interested. I had a student who in fact took my model and developed it in a finite element analysis with the necessary nonlinearity. And in fact discovered that given the large distances, I mean, we talk order of sort of hundreds of millimeters differences, and timescales, large timescales, the finite difference model was less computationally intensive and provided more reproducible and more comparable results to measured results than finite element analysis did. As I said, if I went to smaller elements with much higher heat rates, I would then go to finite element analysis. And there, the issue of nonlinearity, element shape, etc., would be far more important. At this stage, the rectangular element works, and it works sufficiently. Yeah.
Yes, yes.
I hope I've answered your question. But it would be I mean, I can see you and I sharing a cup of tea to have a conversation when viruses allow us.
We are looking forward. Yes, sir. We are looking forward for the collaboration, sir.
when viruses allow us to have a cup of tea together. Yeah. Thank you. Thank you very much.
Sure. Thank you, sir. Actually, I also work on the finite element code, which was basically for the non-linear analysis of the finite element method. So with that, I got so many like corrections when I compare my code with the software. So with that, I developed much more knowledge in that. So I thought it will be whether this code when I will be viewing your code, I wanted to go through whether it can be applicable to that situation or not. Sir, if you give me freedom, I'll go ahead, sir.
I think it certainly is applicable, and it'd be interesting to see. I mean, from we sort of, maybe our minds are too engineering. We tend to say if I can fix it with a spanner, I'm not going to use a micrometer. Yeah. So but I think it'd be interesting. You may well be improving the quality, and particularly at the boundary conditions.
True.
I'm starting to think that the finite element method may well improve the quality of prediction at the boundary condition. I'll happily share the model with you. I have that's certainly available.
Yes,
Thank
sir.
you.
Sure. Thank you, sir. Thank you very much. Shrija, you can go ahead.
Yes, ma'am. Thank you, ma'am. And I request Dr. Sudarshan sir to deliver the vote of thanks.
A very good afternoon and done. So it is my pleasure and privilege to propose the vote of thanks for today's seminar. First, I submit my sincere thanks to our management VJIT, provided the opportunity to conduct the mass event international seminar on advancement in concrete technology. I extended my warm thanks to today's chief guest, Dr. Eunice Balim, Professor, Construction Materials, School of Civil and Environmental Engineering, University of Witwatersrand, Johannesburg. With his busy schedule, he accepted our invitation and held the session nearly 1.5 hours with our researchers and faculty members from various parts of India and abroad. The topic development in understanding heat flow and temperature development in large concrete elements is very useful and very helpful for our researchers and beginners as well as who's working in the area of research. Further, I want to acknowledge thanks to our director, Dr. Saibaba Reddy, and our principal, Dr. Patnaja Madam, and our head of the department, Dr. Pallavi Badri, and other faculty colleagues who are involving in the program directly and indirectly in a grand success. I extended my sincere thanks to Mr. Srinath, Srija, and Mrs. Monica Priya for continuous support and efforts for successful conducting of this event in smooth manner. Last but not least, my sincere thanks to all the participants from various parts of the world for their active participation in the event in a grand success. Thank you. Stay home, stay safe.
Thank you, sir. Thank you, everyone.
Thank you. Can I just say, first of all, again, thank you for inviting me. I hope that everybody found this informative. I certainly hope that there's opportunity, and if anybody works in this area, we'd be very happy to sort of collaborate and just keep us informed. To Professor Badri and to Srija, if I'm pronouncing your name correctly, and to Dr. Sudarshan, thank you very much, and really it was a pleasure talking to all of you. Stay well and be safe and be healthy, and warm greetings to you and your families. Thank you.
Thank you, sir.
Thank you, sir.
Bye-bye.
Bye, sir. So participants, we are having afternoon session also, right? Shrija, can you please announce once?
Yes, ma'am. Yes, ma'am. I'm doing. Participants, you